All right, welcome back, everybody. Today's lesson is on a little bit of history, actually. A lot about how we figured out that plates are moving around, that plate tectonics occurs. Let's start out with surface crustal movement. When climbers in 1953 planted their flags on the highest mountain, they set them in the snow over the skeletons of creatures that had lived in the warm, clear ocean that India, moving north, blanked out. Possibly as much as 20,000 feet below seafloor, the skeletal remains had turned into rock. This one fact is a treatise in itself on the movements of the surface of the earth. If by some fiat I had to restrict all this writing to one sentence, this is the one I would choose. The summit of Mount Everest is marine limestone. This is written by John McPhee in Annals of the Former World. The summit of Mount Everest is marine limestone. That's a pretty powerful statement, especially when you're realizing this for the first time ever, that something like that could be true. So evidence for crustal movement on Earth's surface. This is past evidence. Geologists have looked around the Earth. They've noticed for a long time that rocks are deformed. Originally, we know sedimentary rocks form from flat horizontal layers. However, observations made on Earth's surface indicate that original rock formations have been changed throughout past Earth movements. And the first change we know is tilting. This is where rock layers are found at an angle to their original formation. You can see in this picture they're not horizontal anymore. These rock layers are tilted. Tilted up at an angle to the right. Second piece of evidence, folding. Rock layers are getting warped in these pictures. You can see it. This one fold is a gigantic fold right here. And there's some nice folds right here. And these folds are created by tremendous stress, by pressures on the rock. And the rock doesn't really crack in this case. It just bends plastically. Here's some nice folds in California. Nice road cut, great place to look at rocks. Lots and lots of folds here. You could spend a long time here. Of course, California is in motion. Remember, the San Andreas Fault and all the associated faults around it are moving all over the place all the time. So there's stresses everywhere. Okay, another interesting piece of evidence, displaced fossils. This just means fossils like this fossil shell in the Helderberg Mountains south of Albany, New York. It's not below sea level, obviously. These are marine fossils, like that clam shell or that scallop shell, found at high elevations, and this demonstrates crustal uplift. So the land used to be underwater and has since lifted up above water. Okay, third piece of evidence, subsidence or sinking. Now in this picture, you see that as the soil and rock material is eroded off the mountains here, it eventually washes down and ends up depositing here. And all these sediments build up over time and they become heavy. That weight forces the rock underneath it downwards. This is called subsidence. Now, on the other side of this picture, the opposite's happening too, because the weight of all these particles that's been removed is now less, and so the mountain can uplift at the same time. And sometimes you'll get a mountain uplifting while it's actually eroding, and so it's losing material and gaining height, but sometimes it's also balanced out. The amount it loses is pretty similar to the amount it gains. But this subsidence, shallow water fossils found in rocks near the bottoms of deep oceans prove that rock is sometimes forced deeper into the crust. Good example of this is the Mississippi River Delta, where all that sediment that's being carried every day by the Mississippi River is building up in the Gulf of Mexico and forcing that rock underneath it downwards. Okay, moving on. Faulting. This shows the crust is moving around for sure. Pressure on the rock layers causes them to break. The boundary between the broken layers is called a fault. And you can see in the first picture, there is your fault. right there. Second picture. This fault's at a slightly more laid back angle. And looks to me, it's hard to tell here exactly, but it looks like perhaps this layer here maybe used to match up with this layer here. So if that's true, perhaps this side is rising like that and that side's moving like that. And there are different types of faults, which we really don't have to get into too much in this earth science course. But if you go on further in geology, you'll learn those types. Nice photograph here of a horizontal fault. Looks like a farm field. And you can see after an earthquake that these lines don't match up anymore. They used to, but the earth's moving. So there's a nice horizontal fault, very similar to a transform fault. In the second picture, this is a vertical fault, and this side is moving this way, this side's moving this way. Okay, the next term, isostasy. That's a tough one to say. And this is kind of what I was referring to before about the mountain that's losing material and therefore weight, and it's gaining elevation. Isostasy is this equilibrium, this maintaining of equilibrium or balance in Earth's crust when overlying weight of rock is increased or decreased. And a great example of isostasy is happening right here in New York because we used to be glaciated. We used to be covered with a mile thick of ice right here where I'm speaking a long time ago, maybe 20,000 years ago. And this ice had weight. It was pushing down on the rocks beneath it and deforming those rocks, pushing them lower. Well, ice melts eventually. We know we came out of the ice age. It's good for us. But that weight was relieved, and now rock is rebounding. So the crust in many parts of New York State are still rebounding today. There's actually active faults, small ones, but nonetheless faults, that move as the Earth kind of stretches back to its position it was in before. This is still happening today. Now in the right-hand picture, you can see it looks like we have a mountain range, and you can see the core of it extends deep into the crust and high into the sky. But as it erodes over time, the weight is reduced on the surface because those rocks have been carried away by water, wind, and ice. And the bottom starts to kind of move upwards a little bit. And we notice the same thing here. It's even reduced even more, and the bottom's coming up even more. And so this balance of forces kind of creates a flat land surface eventually. But now this section that was much deeper before is now similar thickness to the parts on this side and this side. So this is isostasy, this maintaining of equilibrium, mainly because of loss of material and changes in weight. And that is it. Quick slideshow today.